Welcome back. We finished up the last video by saying that a system of linear equations can have either no solution or a single solution, or if the equations overlap, infinitely many solutions, but nothing else. It can't just have two solutions or just five solutions. There's two vocab words that we need to attach to these ideas before we move on to some computations. So sometimes with a system of equations, it'll be important to know whether a solution exists and whether the solution is unique. So they'll have the question of uniqueness, and we'll also have the question of existence. And of course, the idea of uniqueness is just to say that there's a single solution. The solution is unique. So when you solve the system of linear equations and there's only one solution, you can say, yes, that system has uniqueness. And the idea of existence, of course, is just, does a solution even exist, which encompasses both having a single solution and having infinitely many solutions. So really those words come out of solving it. Once you solve, you'll know if the system has uniqueness and if it has existence of solutions. So those are the two vocab words. The book will ask you about a few of those in your homework. But let's go ahead and actually move on to doing some computations. So this is example 12 from your homework. It's not one of your assigned problems, but we can make use of it. So notice we're using the x1, x2, x3 language that linear algebra uses instead of x, y, and z, but this is still a three-dimensional system. If you graphed it, you'd get three planes. And if all three of those planes intersected at one point, you'd have a solution. And if they don't, you won't have a solution. Computationally, as we move further on in the course, we're going to solve these things using technology, some sort of calculator or app or something, because it gets tedious, as you know, solving these things. However, I think it's really important for us to have a deep understanding of the methods. So we're going to spend some time solving some of these by hand, only enough time to make sure that we have the deep conceptual understanding that we need. And then we'll go on to technology. But for the moment, let's talk about how we would solve this by hand, linear algebra style. So we've already made one good step of turning it into x1, x2, x3, but after we make that step, you're probably saying, where's the matrix? Because you know linear algebra, if you know anything about it, you probably know it's matrices. So we're going to go a step beyond the x1, x2, x3 and just strip the variables off entirely and the equal signs and turn this into a matrix. Oops, let's get on the right layer here. And you probably know matrices tend to have these brackets around them. Not always, but usually. And then it's just writing down the coefficients. So 1, -5, 4, -3, 2, -7, 3, and -2, -2, 1, 7, -1. This, my friends, is a matrix. It contains no new information from the blue version above. It's just a shorthand notation. So matrix has a couple words that go with it. What we have right here is actually an augmented matrix. And the reason we call it an augmented matrix is it has this column, this -3, -2, -1 column, the equal sign column. That's an augmented matrix. It has the solutions. There will be times when we only care about the left side of the equal signs. So if we ignored this last column right here and just had that much, that would be called the coefficient matrix. I know, mathematicians, so creative. So let's see, let's pick a different color. Let's say if you had just this much right here, that would be the coefficient matrix. In chapter 1, we're mostly going to be working with the augmented matrix because we're working with an actual system of equations. I think that yellow was burning my eyes. It's very bright. Let's go away from that for a minute and then we'll come back to it. So I just wanted to point out that there are 3 different basic tools, 3 different basic algebraic techniques that we're going to use when we solve a system of linear equations in this matrix format. Hopefully all 3 of these will make sense, but it's worth making them explicit. So first of all, it's legitimate to swap 2 rows. I think that makes sense. If you think back to the original equations, it doesn't matter which order you write those 3 equations in. So it's fine to swap rows if that's more convenient. The second operation is scalar multiplication, which just means multiply a row by a constant. That's the equivalent of going back to our example here and saying I want to multiply both sides of this first row by 2. And you know that's okay to do to an equation. As long as you do the same thing to both sides, you're allowed to do anything you want to both sides. So you're allowed to multiply any row of a matrix by a constant. The third one is row sum operation, which says you're allowed to add a multiple of one row to another row. That was a little more complicated, but still think back to our system here. If you multiply one row, it's still equal, still balanced. And if you add equals from one line to equals from another line, it's still equal, right? You're keeping things balanced. So those will be our 3 row operations. This is written on page 6 on our textbook as well, in a slightly different form. But these will be our tools. So let's see if we can use those 3 tools to go actually solve example 12. So let's go back and let's take a shot at this thing. Let's see, I want to get rid of some of this. Let's get on the right layer again. You can tell this is my first video of the new quarter. So I'll get rid of some of that. Let's see, let's get rid of these little yellow lines. Okay, so let's see what we can do as far as solving this system of equations using our 3 row operations. Our basic idea is we are going to want to use x1 in the first row. So we're going to want to use this slot to put a 0 there and put a 0 there. We are then going to want to, once we're done with that, use this slot, x2 in the second row, and put a 0 there. And if there were more rows, we'd keep going, putting zeros kind of below the diagonal. So that's our basic idea. Put zeros below the diagonal. And then we should be able to solve what's left. So let's see if we can go with that. One of our legitimate operations is to add a multiple of one row to another row. So the very first thing I want to do is I want to try to put a 0 right there. And to do that, I would want to add -2 of row 1 to row 2. There's a notation your book uses, so we'll say like -2 of row 1 added to row 2 becomes the new row 2. Okay, so I'm not changing row 1. I am taking -2 of row 1 added to row 2. So -2 times 1 is -2 added to, what's a 0 right there? -2 times -5 is +10. +10 added to -7 is positive 3. Negative 2 times 4 is negative 8. Added to 3 is negative 5. Negative 2 times negative 3 is positive 6. Added to negative 2, positive 4. And I'm also, well, at the moment I'm not changing row 3. But let me just stop for a moment here and say I had a row that was balanced. I made it a little heavier by multiplying it by negative 2, but then I added it to another balanced row. So this second row here is still true, and if you put the variables back on, so it's 0x1 plus 3x2 minus 5x3 equals 4. That's still a true equation. Let's do the same thing with clearing out this third spot right here. This time I want to add 2 of row 1 plus row 3 to become the new row 3. And if you need to write some of this out, that's fine. I'm kind of doing a lot of this in my head. But let's keep going. So 2 times 1 is 2. Added to negative 2 is 0. That was the whole point. 2 times negative 5 is negative 10. Added to positive 1 would be negative 9. And finally, or not finally, but next, 2 times 4 is 8. Plus 7 is 15. 2 times negative 3 is negative 6. Added to negative 1 is negative 7. Okay, so I got zeros below the diagonal, at least in the first column. My next step is to put a 0 right here. So looking at the matrix as it currently exists, it looks like 3 of the second row added to the third row. We'll do that. So now we're going to say 3 of row 2 added to row 3 will become our new row 3. So I'm going to write a new version of the matrix here. Row 1 is not changing. Row 2 is not changing. I'm going 0, 3, negative 5, and 4. What's changing is row 3. So I'm adding 3 of the second row to the third row. 3 times 0 is still 0. Added to 0 is still 0. That's good. 3 times 3 is 9. Added to negative 9 is 0. That's good. And 3 times negative 5 is negative 15. Added to 15 is also 0. And 3 times 4 is 12. Added to negative 7 is 5. Okay, so we've got zeros below the main diagonal. Let's translate this back now. So check, we've done that. We should be able to solve from here if there's a solution. So now we sort of put the x's and the equal signs back on. So the first row would say x1 minus 5x2 plus 4x3 equals negative 3. The next one will have 0 x1s, so I'm not even going to write that down, but it'll be 3 x2s minus 5 x3s equals 4. And the last row is interesting. I'm going to get my face out of the way here. The last row is interesting. Notice it says 0 x1 and 0 x2 and 0 x3 equals 5. So really that just comes down to saying 0 equals 5. We had a shot with these first two equations. That looked like it might be okay. That looked like it might be okay. This one, though, is a problem. 0 does not equal 5. There's no variables in there to make the two sides balance. So assuming we didn't make any mistakes in our computations, we have gotten to an equation that has no solution. This system does not have existence. The solution does not exist. So I think that's good for this video. This video is getting a little long already, but we'll do one more example where we actually do have a solution. And I will see you there.